Hi guys, so we are on our second video and this is our second video on what I call debunking the fear of relative velocity. So our first video was on the problems of interception and our second video is on problems of basically problems of relative velocity, where particularly there are questions where a plane is flying and there's a wind blowing, and because of the wind the direction of the plane changes and there's one particular direction that the plane needs to take, and then you will find questions about boat and water, where there's flow of the water and the boat has to steer in a certain direction to reach a certain point on the other side of the bank. So we're going to do these kind of questions. This is one question that I've taken, which is November 3, question number 6. If you read the question, you will realize that there is a plane which wants to fly from P to Q, and the velocity in still air of the plane is 280 I minus 50 J kilometers an hour. Okay, now first of all I just want to make one thing clear. When we speak about velocity in still air, it's actually the ideal velocity of the plane. If there was no air, if there was no wind blowing, there was no air current, so this is the velocity that the plane would have, and this is the direction also that the plane would end up traveling. So it says, I'll just call it velocity in still air. So let's call it velocity of plane in air, in still air. So I'm just going to just label it VPA, velocity of plane in still air. You can put any label you want, so free to do that. So that is 280 I minus 40 J. Now what I understand from 280 I minus 40 J is that if let's say this is my relative reference origin, so the plane is somewhat in this direction, something like it wants to travel something like this. So where this is like a 280 I and a minus 40 J. So it's like 280 kilometers in every hour. The plane wants to travel 280 kilometers towards the positive x-axis and 40 kilometers down to the negative y-axis. So this is what the understanding is. This is kind of the orientation of what the plane wants to do. So plane, the velocity of the plane in still air is this. So this is the ideal velocity. Now we know that it's never going to be a case where a plane is flying and there's no wind. This will never be the case. So that's why I'm calling it the ideal situation. And because there's always wind, and wind is blowing in a particular direction, and because of wind the plane tends to steer in a different direction. See, it's very simple, because if you've ever noticed, if you've ever experienced yourself walking on the road and suddenly there's a strong wind blowing, so somehow, if let's say you're walking straight and the wind is blowing towards my right, it tends to push me towards the right. Now if it's going to push me towards the right, now we're talking in very reasonable terms. So I want to just travel straight. Let's say it's a very thin path on which I'm traveling and I cannot go, maybe there's dirt on either side and there's a very thin straight clean pathway that I have to travel on. So the thing is that it's going to push me to the right. Now what I'm going to do is, because if I keep traveling straight, it's going to keep pushing me to the right, so my velocity, my true velocity or my true direction is going to be something else. Now to counter that, if let's say this is the orientation that I want to travel straight and it's pushing me to the right, so I would want to steer a little inwards, a little towards the left, so that even if it with the wind blowing and trying to push me towards the right, it's going to eventually make me come back on the straight road. So it's like that. So when a plane flies, let's say a plane wants to go from P to Q, and whatever that P to Q direction is, but somehow if let's say there was no wind, if there was no wind and there was it's just still air, then the plane could steer exactly in the direction of from P to Q, straight in the direction, and there's nothing to push it to the left or push it to the right. It would keep traveling in that direction, it will reach its destination. It doesn't have to steer anywhere. But because of the wind blowing, it might have to change its direction a bit, so that after the push of the wind, it should come back in the direction straight towards Q from P. Now this is how the logic should work. Now see, this is the velocity of the plane in still air, which is 280 minus 40 j. Now this is where the plane intends to travel if there was no air. But there is a wind blowing, and the constant wind blowing at a velocity of 50 I minus 70 j. So the velocity of the wind is 50 I minus 70 j. So the velocity of the wind is something like this, like it's something like 50 minus 70. So it's something like this. It's something like this. 50 minus 70, something of the sort. I am making a very rough sketch, so it's fine. Now see, this is the wind that is going to push the plane. Now clearly it's going to push the plane a little inwards. Do we all agree that? I'm sure it's very easy to understand. It's going to push the plane a little inwards, because see, the wind is not just this. I mean, I'm taking one particular direction just to show you, but the wind is like coming all the way like this. It's trying to push it. So what will end up happening is very logical, that the true velocity of the plane, what will actually happen. See, this is not what is actually happening. This is what the plane wants to do if there was no air. This is how the plane would have traveled. But with the plane, with the wind coming in, it will end up a little inwards. So and that can be determined very easily by taking both the effects, by taking both the effect of the wind and the velocity of the plane in still air, both into consideration. So this is where the plane wants to go, but the wind is somewhat in this direction, something like this. So what will happen is that after the sum of both the vectors, after the interaction of both the vectors summing up, both vectors summing up, the plane will end up traveling in this direction. Now see, it is saying a plane flies from P to Q. Now, which means it is already flying from P to Q. If you just look at the plane, so the plane is already going in the P to Q direction, but it never took off in that direction. The thing what we need to understand is, it steered a little off course so that the wind could push it and bring it on course from P to Q. That's the idea. So P to Q is definitely this direction. This is the direction P. The green arrow is the P to Q direction. This is how the velocity now is, how the plane is now traveling. After the wind pushing it and after interaction with the wind, this is the true velocity of the plane right now. So this is how the plane is ever. Now the plane, what the plane had done, would have done, was that it traveled, it steered a little outwards. This was the velocity of the plane in still air, and with the velocity of the wind in this particular direction, it ended up being steered directly from P to Q. That's how it is. So which means that the true velocity of the plane, which I am calling this the true velocity because this is exactly what is happening right now. So the velocity, the true velocity of the plane, which I can for this moment I can call it velocity PQ in what is happening right now, is basically the vector sum of the plane in still air plus the velocity of the wind. Okay, because I think these two p's will get mixed up, so let me call this the true velocity. Let's call it the true velocity, which is the true thing that is happening right now. So this true velocity, which is this one, is basically the vector sum of the velocity of the plane in still air and the velocity of the wind. Both vectors interacting, giving you this what is happening now. So this is where the plane had intended to travel as well. So that's why the plane had to steer a little inwards, so that the wind, because with the interaction of the wind, it could come exactly on course from P to Q. That's the idea. So the bearing of Q from, so for the bearing of Q from P, the bearing of Q from P, which means that what we need to find is this angle. The bearing of Q from P is this angle, the whole angle. So for that I need to know the direction PQ, the vector direction PQ, vector PQ, and that I'll get from the true velocity. So if I can get the true velocity, I know exactly where the plane is headed at the moment. So the velocity of the plane in still air, which was the ideal condition, was this. Then the wind came in, interacted with it, summed up, and now what is happening is that it is the velocity of the plane in the true direction is 280 plus 50, 330, and minus 40 minus 70 is minus 110. This is the true velocity of the plane, and therefore this has to be the direction PQ. So the direction PQ is basically this, or I can say maybe the displacement vector would be in this direction. So how do I find the angle? What I'm going to do is, with the help of what I have at the moment, that the true velocity of the plane is basically 330 I minus 110 j, which means 330 towards the right. Every hour it's going 330 kilometers towards the positive x-axis direction and 110 kilometers towards the negative y direction. So I can, with the help of these two values, I can find out this angle right here, and I'm going to call this angle, let's say, alpha. So I'll say tan alpha is opposite upon adjacent, which is basically the j component upon the I component. So 110 upon 330. I'm not taking the minus sign because the minus sign is only giving me an orientation. I'm just taking this particular triangle when I'm saying this is 110, this is 330, and I need to find out this angle alpha. This is P, this is Q. This is what I'm trying to do. So I'm trying to get that out. So I mean, obviously Q is not exactly here, it's somewhere ahead, but this is the ratio that I'm getting from the triangle. So I can find alpha. If I can find alpha, I can add the 90 to the alpha and I can get the entire bearing. So this comes out to be, I need to calculate it. So inverse tan of 110 by 330 comes out to be 18.43 degrees. So therefore the bearing of Q from P, bearing of Q from P is then 90 plus 18.43. So that's 90 plus 18.43, and that's 108.4 degrees. So this is where the plane is headed. Now the next part is the time of flight to the nearest minute, given that the distance PQ is 273 km. So PQ, let's say Q, which is not exactly here because I just, for the convenience of understanding vectors, I just made it. So maybe Q is in the same line, Q is, let's say, somewhere here. So it's exactly 273 kilometers from P to Q, and now that I have the true velocity with me, I can find out the magnitude of this velocity, and from that I can easily find out the time. So from the vector I can find out the true velocity magnitude, and that would be 330 square plus 110 square whole root, and that would be 330 squared plus 110 squared root. That's 347.85 something, but this is, I think, good enough number of significant figures. Guys, try to take intermediate answers to at least 4 to 5 significant figures, because your final answer is to be given to 3 significant figures. So it's always good to take the intermediate values to more than 3 significant figures, because if you don't do that, you will get rounding error at the end. So the time of flight, so we know that velocity is equal to displacement upon time, so time is displacement upon velocity. So the displacement, which is basically the distance PQ, is 273. So 273 divided by 347.85 should give me the number of hours. So 273 divided by 347.85 gives me 0.785 hours, and we can always write it in minutes into 60. We can always write in minutes, and it's around approximately 47.1 minutes. So that's the time of flight. Okay guys, I just realized that the previous question that we did, the last part answer, the time taken to travel from P to Q was required in the nearest minute. So I gave the answer 47.1. So actually the answer should have been stated 47 minutes, not 47.1. So I forgot that it was to the nearest minute. Okay, so we are on the next question, which is very similar to the one that we just did, and it's from November 07, question number 5. And if you read the question, you realize that there is again a plane which is traveling from P to Q. I don't know what's with P and Q, but traveling from P to Q, and the plane flies from P to Q, where PQ displacement vector is already given to you. Now this is the PQ displacement vector. That means this is the direction which the plane is actually traveling. Okay, so and that direction is 960I and 400J. So PQ is 960I and 400J, which is something like this. If I were to make 960I and 400J, so it should be something like this. It's something like this. I mean, I'm not very accurate, but something in this direction. This is where, so let's say if P is here, then Q is, let's say, somewhere here. So this is the direction in which you have PQ. So vector PQ is 960I 400J. So a constant wind is blowing with velocity minus 60I and 60J. Again, so there's always wind. It's never still air. That's the ideal condition. So the wind velocity of the wind is apparently minus 60I 60J. So see, I'll explain it to you over here what minus 60I 60J would mean. It would mean that the direction of the wind is something like this. This is the direction of the wind. Minus 60I plus 60J. But obviously the wind is everywhere and it's all in this direction. It's something like this. And again, it's very reasonable to say that the plane actually must have started off somewhere in this direction, or maybe somewhere in this direction. Then because of the wind, because the wind is blowing this way, it was pushed on course from P to Q. That's the simple logic. So it is right now traveling from P to Q. So this means this is right now what is happening. This is the real velocity of the plane. This is the true velocity of the plane, not the ideal one. This is the true one. And the ideal velocity of the plane must have been something else and must have been somewhere in this direction, not here, because here, if it was here, the wind would have pushed it further away from PQ course. So it had to be somewhere here or maybe here, that because of the wind blowing in that particular direction, it was pushed on course towards Q, from P to Q. So now I don't know where it is, but let's say I make it here, or maybe I can just make it here, maybe. So something like this. Maybe it was something like this. This was the velocity of the plane in still air, that we call velocity of the plane in still air, which is the ideal velocity of the plane. Must have been something like this. And because of the wind blowing in this direction, this is, we can take the velocity of the wind. The plane wanted to go here, because of the wind it was pushed, so the ultimate velocity became exactly on course from P to Q. So this is the velocity, the true velocity, I call it the true velocity, which is exactly what is happening at the moment. And this red one is the velocity of the plane in still air, we generally call it, I'm labeling it as PA, velocity of plane in still air. And let me just clear this out a bit. This was just to give you an orientation of what's going on with the wind. The blue vector is basically representing the velocity of the wind. Now again, the true velocity will always be the velocity of the plane in still air plus the interaction of the wind. So we would say velocity of the plane in still air plus the velocity of the wind will give you the ultimate true velocity of the plane, which is in the direction PQ, because that's where the plane needs to travel. It has to go from P to Q. So this time, in the last question, what happened was there we knew the velocity of the plane in still air, we knew the velocity of the wind. This time we know the velocity of the wind, but we don't know the velocity of the plane in still air. That's what they're asking in the question, but we know the true velocity. We actually don't know the true velocity, but we can easily find out the true velocity because we know the true direction. We know the actual direction PQ, which is 960I plus 400J, which is also the displacement vector. Now you know that velocity is equal to displacement upon time. So if I intend to find the velocity vector, I just need to take the displacement vector and divide it by time. And they have already told us that the plane takes 4 hours to travel from P to Q, which means I just need to take the velocity, the displacement vector and divide it by 4, and I should get the velocity vector. So 1/4 of 960/400. This is how we write it. We generally don't say 960/400 upon 4. That's not an appropriate symbol. We can use it sometimes, but this is a better way of writing it. So I'll just say 1/4 of 960/400, which is basically the displacement vector divided by 4. So this turns out to be 960 divided by 4 is 240, and 400 divided by 4 is absolutely 100. So this is the velocity vector. The velocity of the plane in the true velocity, sorry. This is the true velocity. What is exactly happening at the moment? This is the true velocity of the plane. Now we need to find the velocity of the plane in still air, which you know then would be the velocity of the plane in still air would be the true velocity minus the velocity of the wind, and that would be 240, 100 minus the velocity of the wind, which is apparently minus 60, 60, and I think this should turn out to be 340. This is the velocity vector in still air, 340. And we have to give it in I and J form. The question particularly says that. We don't read the answer this way, so you'd say the velocity vector in still air, which we are labeling as this, is 300I plus 40J. That's our answer for part 1. And the next part says the bearing to the nearest degree on which the plane must be directed. Okay, now see guys, you need to understand, it's saying the bearing that of the plane that must be directed. Now see, the plane cannot start off heading towards Q from P, because the pilot knows and the control tower also knows there is going to be wind. So the wind is going to push the plane. If it started off in this direction, the wind would have pushed the plane and the plane would have gone somewhere like this. But we don't want the plane to go in this direction, we want the plane to go in the PQ direction. So that is why the plane was steered a little inwards, so that even with the push of the wind, both the vectors interacting, summing up, it would fall exactly on course from P to Q. So the bearing to the nearest degree on which the plane must be directed, that means they're basically asking where would you want the plane to start off, so that after the wind pushes it, it would come on course. So this is the, basically they're asking us for the bearing of the velocity of the plane in still air, which is this angle, and I think we can easily find that out because now we have the velocity vector with us. So from the velocity vector I can easily find out this small angle. Again I'm going to call it alpha. This small angle right here I'm going to call it alpha, and this would be simply tan alpha would be opposite upon adjacent. Opposite is the j vector and adjacent is the I vector. So that's 40 over 300, which implies alpha turns out to be 40 divided by 300 inverse tan, and that's 7.59 degrees, which means our bearing, which is the red angle that I marked here, the bearing would then be 90 minus 70.59, 90 minus, that gives us 82.4 something. We have to give the answer to the nearest degree, so it's basically 82 degrees.